cellular functions of proteins. So proteins means of first importance. The Latin for protein is of first importance. So proteins are of extreme importance in a human body. Okay? They play crucial roles in all our biological processes. All our enzymes are made of proteins. Okay? Proteins are polymers of amino acids. Polymers are links of monomer units, remember? So every amino acid, when it links together, that's what forms a protein. It's just all these amino acids are linked together. It could be 10, could be 20, could be 1,000, depending on the size of the protein. Okay? Proteins have important biological function. Enzymes are biological catalysts. Normally in the lab, we can heat things up, make a reaction go faster. Can't do that in the human body. Can't heat our bodies up to make reactions go faster. So we have catalysts. We have enzymes. Enzymes function as catalysts. They bind to something, make the reaction occur, become unbound to it, and release themselves back in the soup so we can use it over and over again. So these catalysts allow the reaction to occur at a fast rate without heating our bodies up. And that's why enzymes are so important. These proteins also form antibodies. Antibodies are your immune system, your defense proteins. Okay? They're also transport proteins in the blood. They transport hormones from one part of the body to another. They transport all kinds of different things that need to be moved from one portion of the body to another portion. Okay? Regulatory proteins that regulate your metabolism, regulate how your body responds to things. And structural proteins, building of the cells, building of your replacement of your skin, replacement of the connective tissue, building of your bones. Okay, your structural proteins build these back up. So these proteins have a lot of functions in your body. Okay, movement proteins, so the scaffolding, the cytoskeleton in your cells allow the cells to move. Okay, building up of the tendons in your body that allow for movement and pulling on the muscles. Okay, nutrient proteins provide the body with nutrition. So you can see these proteins have many, many biological functions, and they're all extremely important to the human body. Angiogenesis inhibitors is proteins that inhibit tumor growth. This is some of the new research they've been doing. Okay, so we have proteins that actually stop tumors from growing. Now remember, cancer is a tumor. And the reason we have trouble with cancer is our own cells that grow at a rapid rate. So there is no magic bullet now. Okay, the cancer cell is our regular cell. There's no way to identify it that we know of in a lot of cancers. Okay, so to inhibit it would be great. That's why chemotherapy makes people so sick. Chemotherapy, you give the person a drug that's toxic to all the cells of your body. It's also toxic to the tumor cells. Hopefully the tumor dies before the patient. That's what chemotherapy is. Okay, you gotta remember, because cancer cells are your own cells. There's no difference between them, just growing at a faster rate. Okay? So cancer research have long known that solid tumors cannot grow larger than the size of a pinhead unless they stimulate the formation of new blood vessels. They have to have their own blood supply to grow. They start growing, and then if they can't get nutrition to that tumor, they're not going to grow you're not going to grow. Okay? So they have to stimulate the formation of new blood vessels that provide the growing tumor with the nutrients and oxygen and remove the waste products like carbon dioxide of cellular metabolism. Okay? So they got to form a system where they get nutrients and they give off their waste products. Okay? So angiogenesis. Angiogenesis is the formation of new blood vessels in normal tissues. Okay, so if we can stop the formation of blood vessels, we can cut off the tumor's blood supply. We can cut off its food supply. Okay, this is the new concept for anti-cancer drugs now. Rather than going after the cells themselves, because there's no difference between the tumor cells and our cells. Okay, now we're going to go after stopping the formation of new blood supplies to it. And that will slow down the cancer growth. Okay, so angiogenesis occurs through a carefully controlled sequence of steps. Okay, in addition to growth factors that stimulate the process, there are several other proteins that inhibit the formation of new blood vessels. Okay, so the normal process of angiogenesis is dependent on the appropriate balance of the stimulatory growth factors and the inhibitory proteins. Remember, the body, we have systems that work to do one thing and systems work to do the opposite of it. You have to be able to trigger something to occur and then stop that from occurring. Okay, body has to work both ways, just like with insulin we produce and glucagon we produce. Insulin takes sugar out of the bloodstream. Glucagon puts sugar back into the bloodstream in case you're hypoglycemic and you're hyperglycemic. Okay, so all of our proteins, all of our enzymes, and all our hormones have to be able to stimulate and to deaccelerate it. Okay, and that's what we work. That's these processes here. You have to have a stimulatory growth factor and an inhibitory growth factor, and inhibitory proteins. So cells of the tumor secrete one or more growth factors known to stimulate angiogenesis, the formation of the blood vessels, so they can continue to grow. So the newly formed blood vessels provide the cells of the growing tumor with everything they need to continue growing and dividing. They provide them with oxygen, with nutrients, and they take away the products of cell metabolism, and carbon dioxide. Metastasis. Metastasis is what happens when a tumor grows and then it spreads. Gets into the bloodstream, gets into the lymph system, travels through and goes to a new site. Okay? One of the main sites we find with breast cancer. In the 30 years I've been doing dentistry, I've diagnosed six cases of breast cancer. Okay? It shows up on dental x-rays. One of the main metastasis sites of breast cancer happens to be the jawbone. So when I find tumors enough, when I do Panorex, I can see it. You can say that could be a positive metastasis and you get the patient checked. So metastasis also requires angiogenesis. You have to be able to build those blood vessels so this tumor can grow and metastasize. Metastasize just means it travels through the body to a new site and starts a new tumor there. That's what metastasis means. Usually through the bloodstream or through the lymphatic ducts. Okay, so those tumors having blood vessels are more likely to metastasize because they're growing bigger. And they have an access point now. They can get into the bloodstream and send those metastatic cells or cancer cells to different parts of the body. Okay, so clinically, treatment of these tumors has a poor outcome. Once a tumor is metastasized, treatment becomes a lot poorer outcome because now you got different centers and it's spread throughout the body, and it's much, much more difficult to treat. Okay. So proteins that inhibit blood vessel formation could be used as a weapon against developing tumors. So again, you're targeting the faster growing tumor cells and you're not targeting the normal human cells, which is what you want to do. So if this hypothesis turned out to be supported by experimental data, there'd be a number of advantages to using angiogenesis inhibitors, which makes sense to us. Okay, that's where a lot of the new research is heading right now. Because these proteins are normally produced by the human body, they should not have the toxic side effects caused by so many anti-cancer drugs. Remember, anti-cancer drugs, chemotherapy, are toxic to both drugs, both the tumor drugs, the cancer cells, and the human cells. And you're just going to see who dies first, the cancer or the human. They're extremely toxic drugs. Now, these angiogenesis ones, the angiogenesis inhibitors, those are not toxic to the human cells. We make those our own in our body. They're going to have other side effects, yes. There could be other problems we're going to come across, but they're not the toxic chemotherapy drugs we've been using. Okay. Angiogenesis inhibitors can overcome the problem of cancer cells drug resistance. Because again, once a cancer cell can overcome drug resistance, just by evolving, just like bacteria cells do, then it's going to continue going. The more you use a certain drug, the more chance you get of resistance to it. But in angiogenesis, you're not killing the cell. You're not allowing the cell to form blood vessels. So it can't grow. You're restricting its environment. It doesn't have the environmental resources to grow anymore. So you're not getting the problem of drug resistance, which is really cool. So that's becoming a really big problem right now with antibiotics that we're using. Because antibiotics we feed to cattle, we feed to chickens, we feed antibiotics to every kind of all kinds of farm animals, so we can get more money for the meat that they produce. Don't get sick, okay? And that's producing a lot of antibiotic-resistant bacteria. Okay, we treat antibiotics on everything. Okay, so most cancer cells are prone to mutations, and mutant cells resistant to the anti-cancer drugs that we develop. Remember, cancer drugs are doing what? They're growing at a much more rapid rate than normal cells, so they're evolving quicker. So the chance of mutation is going to be much faster in a cancer cell than in a human cell. So they're going to evolve to resist anti-cancer drugs at a much more rapid rate than a human cell, than at a quote, healthy human cells going to. Okay. So the angiogenesis inhibitors target normal endothelial cells, which are genetically stable. So we're not worried about drug resistance. Okay. As a result, drug resistance is much less likely to occur. Endostatin is one of the anti-angiogenesis proteins. That's one of our new drugs we're trying out. Okay. Discovered in 1997, is found to be a protein about 20,000 grams per mole. 20,000 grams per mole is big. Remember your general chemistry? I know you want to forget it, but remember general chemistry? We did molecular weights, like sugar is 180 grams per mole. That's a big molecule, C6H12O6. Carbon dioxide is 44 grams per mole. Oxygen is 32 grams per mole. This thing's 20,000 grams per mole. That is one big molecule. Okay, it's one big protein. Okay, experimental endostatin is a protein inhibitor of tumor growth. It stops the blood vessels from forming, angiogenesis. It binds to the heparan sulfate proteoglycans of the cell surface and interferes with the growth factor signaling. So it stops the signaling of the growth factor, which is coding or binding to receptors to stimulate more blood vessel growth to the tumor area. Okay. As a result, growth and division of endothelial cells is inhibited and new blood vessels are not formed. So the cancer cells, tumor cannot grow anymore. It can't get the nutrients to grow and it can't get rid of its waste. So angiostatin, okay, is another anti-angiogenesis protein. Can't say that real fast. Normally found in the human body. Okay, 1994, this one's 50,000 grams per mole. So these are large molecules. Okay, it's even double the size of the other one. So the role of angiostatin in the human body is to block the growth of diseased tissue by inhibiting the formation of blood vessels. So that's one of the things that we produce in our own body. Like endostatin, it's hoped that angiostatin will block the growth of tumors by depriving them of their blood supply. That's kind of neat. It's kind of new, the new research that we're heading towards. And it's a new way of approaching things that we could hopefully use and get rid of some of these big toxic side effects we have with cancer treatments. Right? I mean, the more weapons we have at our disposal, the better off we're going to be. All right, the alpha amino acid. Remember what alpha means. Alpha, beta, delta, gamma, epsilon, and so on. So you count the Greek alphabet. Alpha means the carbon next to or adjacent to the carbonyl group. So there's your carbonyl group, C double bond O, and the carbon next to it. Let's say that's a hydrogen. There's your carbon. That's your alpha carbon. Okay. So these are alpha amino acids. Okay. So name implies these compounds contain both an amine and an acid, amino acid. Okay. Hundreds are formed naturally and synthetically. Okay. We have hundreds of amino acids formed, but the body only uses 20. Okay. There's only 20 are common in nature that our body uses. So every protein we have, those endosin, the anti-angiogenesis proteins. Okay, I mean 20,000 grams per mole, 50,000 grams per mole. They're all made up of only 20 amino acids. It's just the order that determines what type of structure is going to be made, what type of protein is going to be made, and that order is determined by DNA. And we'll show you exactly how that's going to work. Okay, all 20 are what's called alpha amino acids. That's the carbon next to the carbonyl group. Okay, alpha means the amine is adjacent to the carboxyl group. Okay, right next to the CO group. Okay, 19 out of the 20 are what's called stereoisomers. We talked about stereoisomers, like your hands are stereoisomers of each other. Okay, they're non-superimposable mirror images. So only one of them is not a stereoisomer. And that's because it does not have a chiral carbon at the alpha carbon. Okay, because that's glycine. Glycine has a hydrogen, which puts us two hydrogens. We'll show that in a second. But all the amino acids are stereoisomers because they have a chiral carbon on their alpha carbon. Okay, except for glycine. There's only one. That's because it has a hydrogen, not a carbon. And we'll get those in just a second. So amino acids. Okay. Attach the alpha carbon, okay, to a carboxylate group. Carboxylate group is COO. That's your carboxylate group. A protonated amino group, NH4 plus. Okay. And a physiological pH, the amino acid has a proton on it. So physiological pH, the carboxyl group is COO minus, which is the pH of the bloodstream, and the amino is NH3, NH3 plus. Okay. A neutral molecule equal to a positive negative charge is called a Zwitterian ion. So Zwitterian ions simply means a molecule has the same number of positive and negative charges, so it's neutral. Okay. At the carboxyl end of the amino acid, you're going to have a negative charge. At the amino end, you're going to have a positive charge at physiological pH. That's 7.3, 7.4. That's what you're going to have. You have one negative charge, you have one positive charge. One minus, one plus, it balances. That's a neutral charge. That's what a Zwitterian ion is. A Zwitterian ion has the same number of positive and negative charges, so the total net charge is 0. So it is neutral. Okay. And this is your amino acid. This is a carboxyl group. This is your carbonyl group. This is your amino group. This is your hydrogen. This is the alpha carbon right here. Remember, alpha carbon next to the carbonyl group. Okay. And here's your R group. So all amino acids have this exact same structure. The only thing different on the amino acids is this right here, this R group. That's the only difference. That's your side chain. All amino acids have the exact same structure: a carboxyl group, amino group, a hydrogen, and an alpha carbon. Now, if that R group is a hydrogen, you lose the chiral carbon at the alpha carbon, because now you got two of the exact same things attached. So it's not a stereoisomer anymore. But every other amino acid, that R group is something different. And there's 4 different things attached to the alpha carbon. Therefore, this gives you a chiral carbon right here. That gives you a stereoisomer. Okay. Everybody understand that important part we're going to be dealing with. Someone throw a thumbs up or give me a yes or. Make sense? Cool. Perfect. All right. So, the alpha carbon of each amino acid is also bound to a hydrogen atom and a side chain. That was our R group. Okay, so you have the carbonyl group, your amino group, the hydrogen group, and then your R group, which is your side chain. Okay, so in a protein, the R groups interact with one another through weak attractive forces. Either they're London dispersion forces, it could be hydrogen bonding, it could be sulfur by disulfide bonds, it could be a number of interactions that they exhibit. Okay, so these interactions participate in folding the protein chain into a precise 3-dimensional shape that determines its function. Everything works on shape. Okay? The substrate or whatever has to be dissolved has to bind to that protein. It has to bind to it by having the correct shape to fit inside that protein, so they can be modified into that enzyme. Okay, so everything folds in a specific shape. So if we mutate something and the shape doesn't fold right, we got problems, because everything works by shape in the body. All the receptors bond to a specific 3-dimensional shape. So they serve to maintain this 3-dimensional conformation. Okay, so all the amino acids that line up, all those R groups now have bonding that forms and shape this protein or enzyme or structural protein or regulatory protein, whatever it is. They form this shape, and that gives us its function. So Zwitterian, remember Zwitterian stands for same number of positive and negative charges so that the compound is neutral. Amino acids are a white crystalline solid, high melting points, and high water solubilities. They've got plus and minus charges on them. They're polar. They're going to dissolve in water. Okay, high water solubility because of the polar ends. Okay, high melting points. Again, they're polar. They're going to stick together. You got a positive end and a negative end. You got a positive and negative on the other one too. Opposite charges attract. they're going to be held together. So amino acids are going to have high melting points, which you would expect, okay, and high water solubility because of their polarity. Okay, so the two charged group, the basic amino acid group, then NH3 plus, and the carboxyl group, the COO minus, at the two ends lead to internal proton transfers. All that means, it's a fancy way of saying you have COOH at one end, carbonyl carbon, and then NH2 at the other end. This is your H, this is your R group here. Okay, there's your amino acid. So an internal proton transfer, okay, at the physiological pH, this hydrogen transfers over to the amino group, giving you NH3 plus. There's your chiral carbon. CO minus. There's your zwitterion. It's an internal proton transfer. Proton is just a hydrogen atom. So the hydrogen moves from there, from the acid to the base, because you're in a basic environment. You're in the 7.3, 7.4. You're slightly basic to neutral pH in the body. Okay? So you have two charged groups now, your zwitterion, because of the pH of the body, and it's an internal proton transfer. It's a transfer from the proton within the same amino acid. Okay, and those are zwitterion ions. Plus and negative charge are balanced. Exactly. So by changing the pH, you can change the net charge on these zwitterion ions. So if we change the pH to an acid environment, okay, they wouldn't have charges because the H would protonate back onto the carboxylic acid, and you'd lose the H off the ammonia group. So you can change it by changing the pH, changing its environment. The pH at which there is no net charge is what's called an isoelectric point. Okay, that's what we can use to do amino acid separation by electricity, by charge we put through the solution. And the pH, when there's no net charge, okay, when the proton is the acid has a proton, and the NH, it's just NH2 on the other end, that is called your isoelectric point. Okay, we talked about stereoisomers. Okay, the alpha carbon of all amino acids is chiral, except for glycine. In glycine, the R group is equal to H, is a hydrogen. Therefore, there's two hydrogens on the alpha carbon. Therefore, two of the same thing, you cannot be chiral. Okay, so the alpha carbon of all amino acids is chiral except for glycine. Okay, glycine is the only common amino acid that is not chiral. Amino acid configuration is isolated from proteins. It is in the L form. Remember, we had D and L isomers. We have stereoisomers. Okay, so amino acids isolated from all our proteins are in the L stereoisomer. We draw most oxidized ends of the molecule, carbonyl at the top. So the most oxidized ends of the molecule, the carbonyl goes to the top. Remember how we do our Fischer projections in the last chapter, drawing our sugars? Okay, the most oxidized end is up on the top. Okay, so here's your most oxidized end. Okay, and this is glyceraldehyde, and this is D-glyceraldehyde, L-glyceraldehyde, because the OH group is to the left, OH group to the right. It's the OH group farthest away from the most oxidized carbon. Remember how we did that? The OH group that's farthest away from the most oxidized carbon determines our D or L enantiomer. Okay, so this is L-glyceraldehyde, and this is D-glyceraldehyde. And here's your aldehyde group. Now we're going to do the same thing with our amino acids. This is an L-alanine amino acid. This is D-alanine. Okay, alanine has a CH3 as its R group. Okay, except now we're not using OH group. We're going to use the amino group. So the amino group to the left is L, to the right is D. Okay, so we're doing the same thing we did with these are our Fischer projections up here at the top. Same thing we did before. Same exact way we're going to put it down, except instead of the OH group determining our D or L enantiomer, it's going to be the ammonia group, the NH3 group. That's going to determine it. If the NH3 goes to the left, it's an L, levitory rotation of plane polarized light. If the NH3 goes on the right, it's dextrorotary. Okay? It's D. Rotates plane polarized light to the right. So that's how we determine D and L enantiomers for amino acids. Okay, again, you see L-alanine. You see this is the ball and stick model. This is your ammonia group to the left. This is your ammonia group to the right. So you have L and D. Okay, and you can see those are non-superimposable. You can't line those up. So almost all alpha amino acids isolated from proteins have the L configuration. Almost all monosaccharides, all the sugars, have the D configuration in our body. So all of our amino acids, basically from proteins are made up of L configuration amino acids. All the sugars in our body have the D configuration. All right, so class of amino acids. All differences between amino acids depends on their side chain, the R group. So if we're going to classify amino acids, whether they're neutral, acidic, basic, whatever, the only difference, remember, the only difference in amino acid is the R group. So the R group is going to determine the differences. That's the only that's different. Okay. So when we classify them, it's going to be because of the differences in their R group. Okay. Amino acid group based on the polarity of their side chains of the R group. Okay. They can be nonpolar. They can be polar. Neutral have a high affinity for water, but are not ionic at pH of 7. Okay. The neutral ones have the thinner, but they're not ionic at a neutral pH. Okay. And negatively charged. Okay. Negatively charged have an ionized carboxyl group in their side chain, making it acidic, and positively charged. So you have 4 different types you can classify. They can be nonpolar. They can be polar, where they have a high affinity for water, but are not ionic at a pH, a neutral pH. Okay. They can have negative charges on them, and they can have positive charges on them. Okay, makes sense? The four different types, 4 different classifications are nonpolar, polar, okay, negative charge and positive charge. Which shall we break that up? And every amino acid, each of the 20 amino acids, they all have a 3-letter abbreviation. So alanine is an amino acid with CH3. It's called ALA, ALA. Glycine, the one that has hydrogen on it, is GLY. Okay, you need to memorize all these amino acids. I'm just kidding. Don't memorize. I'll give you this chart. You'll have this chart available on the test. I don't like memorization. I really don't. I promise you, when you graduate and you go look for a job, there is nobody out there that's going to pay you to go, oh, memorize this list for me. It doesn't happen. Okay, memorize. You can always look it up. Look at Google. I mean, you can look it up in 5 seconds. You know, no one pays you to memorize. So understand how to read this little chart and understand that there's 3-letter abbreviations. And if you want to look at, say, let's look at histidine. Histidine is HIS. Serine is SER. Tryptophan is TRP. So we use these 3-letter abbreviations putting together our proteins, and you just know we can go back and find out what they are using this chart. Okay. So hydrophobic non-polar amino acids. These are your, what is there, 5? There's 9, right? Yeah, there's 9. There's 9 non-polar amino acids. And look at the R groups. Remember, the only difference here is the R groups. I understand there's charges up here, NH3 plus, CO minus, but they're the same in every one. So that's not a division. That's not a way of defining them. So look at the R group. If the R group is non-polar, these are non-polar amino acids. R group in glycine is H. That's non-polar. Methyl group, CH3. CH, 2CH3 group, CH2. See how these are divided? Hydrocarbon, benzene ring with a CH2 group. Here's the little ring structure. Here's another structure. That's tryptophan and CH2 with the sulfur group in there. Those are all non-polar because the R group is non-polar. Remember, the only difference between amino acid is the R group. So that's what we use to determine the classification we're going to use. So all of these are non-polar amino acids. Okay. Polar neutral amino acids means they're polar, but they don't have a charge on the R group. So you had non-polar, now you have polar neutral amino acids. There's an OH group here. OH is polar, but there's no charge on the R group. Remember, don't worry about these charges here, okay? Because that's there on all of them. We're only looking at the R group to classify the amino acid. The first ones were non-polar. Now these are polar. There's an OH group. Here's an OH group. Here's an OH group. Here's an SH group. Here's a carbonyl group with an oxygen here. Carbonyl group, nitrogen, too. Okay, those are polar groups. Okay, so those are your polar neutral amino acids. Then you have charged amino acids. You have negative charges and you have positive charges. Okay, there's a negative charge here. There's a negative charge here on glutamate and aspartate. Okay, you have positive charges on lysine, arginine, and histidine. Okay, those are positive charged amino acids and negative charged amino acids. There's your 4 divisions right there. Do not get confused. 50% of the students are going to miss it because they're going to, oh, there's a positive charge here and a negative charge here. It's polar. No. Okay, don't count the main structure. The only difference between all the amino acids is the R group. So if the R group is neutral, it's nonpolar. If the R group is neutral nonpolar, it's like a hydrocarbon, it could be that classification. If it's polar with no charges, it'd be another classification like OH or NH2. If it's negatively charged polar, then it's going to be the negatively charged ones or positively charged amino acids. And all that depends upon the R group. And that's how you classify amino acids. Those are the 4 classifications. Okay, so write the 3-letter abbreviation and draw the structure of each of the following amino acids and determine which is polar, non-polar, acidic, or basic. Okay? So we should be able to tell that. Remember, those classifications are only based on the R group because everything else is exactly the same. All right, so let's draw, what are we drawing here? Glycine. Glycine was the three, we memorized the chart, right? The 3, no, the chart said glycine was GLY. Okay, so there's glycine, GLY. And now we're going to draw the structure of it. So all we're going to do for every single one of these is you're going to draw, then they line up the same order. NH3 plus, bonded to carbon, bonded to hydrogen, bonded to COO minus. You're going to do that every single time and draw a line. That structure is the same for all amino acids. And glycine has an R group that is hydrogen. So this happens to be a hydrogen. This is our only one that is not achiral, does not have a chiral alpha carbon. So it's the only one that is not a stereoisomer. Okay? And that's how you draw them. You always put the nitrogen on the left, carboxyl group on the right. Every time. You draw this structure every single time first, and then you add your R group. Okay? So there it is drawn with the bigger picture. That's much nicer than I can draw. Okay, so take some of those away. All right, so we always draw this first. This is going to be the same for every single amino acid, so no one should miss this. You draw that as soon as you draw amino acid, and then you just attach the R group. Glycine, the R group is a hydrogen. Okay, and it is nonpolar. Why is it nonpolar?
Because there's no polar R group.
Perfect. There's no polarity to it. It's a hydrogen. It's a nonpolar amino acid. Cool. All right, proline. Now I do not have these memorized. So proline I think is PRO actually. So proline is PRO. That's the 3-letter code. So when we write our amino acid order, we're going to write PRO because you're not going to write all these amino acids out. This gives me a pain in the butt to keep doing that. Okay, so you're going to use a 3-digit abbreviation. So that's proline. So we're going to draw our similar code again. Remember, we can draw NH NH3. We're going to draw our line, our carbon with our hydrogen, our carbonyl group, and our carboxyl group. And then we're going to add the R group. You do that every single time. So here's what you draw. Okay. This is right here. Here's what we drew. There's our structure. Okay. And then we added the R group. And the R group in this case is 2 CH3 groups, making a ring structure. A 5-member ring. Okay. And what type of amino is this? Non-polar, polar, positive or negative? Which type?
Non-polar.
Non-polar. It's a hydrocarbon chain. Okay. It's a non-polar amino acid. Perfect. Okay, making sense? Don't make these harder than they are. 3NN. 309 is, I think it's THR, is it? Yeah, THR. Okay. THR is a 3-letter code. And we're going to draw the same thing we did before. Here's our nitrogen group, our carbon, or CO. We draw this every time. And we draw our line and add our R group. Okay. And then this is the R group for 3NN. Okay. So is this going to be polar? Is it going to be non-polar, polar, positive charge, and negative charge? What do you think?
Polar.
Polar, perfect. That one's going to be polar because of the OH group. You got it. Aspartate. Aspartate is ASP. That's a 3-letter code. Okay. Draw our structure first and then add the R group. Okay. So here's what we draw every single time. Start with the nitrogen, work our way across. No one should miss this on the exam. Okay. You should be able to draw that and then add the R group to it. And again, the R group is in all the lists of amino acids. Okay. So, and then we added our R group. This is our R group. This is our R group non-polar, polar, negatively charged, or positively charged. This one's not tough, guys.
Negative.
Negative charge. Perfect. Exactly what it is. Okay. Like I said, don't make this harder than it is. Just draw the circles of what you want to look at, and that's a negatively charged amino acid. Polar, it's a negatively charged polar amino acid. This is acidic. Acidic are the negative charge, basic are the positive charge. Okay. Lysine. Lysine is LYS. Okay. And we draw. We draw our structure, and then we add our R group to it. Okay. There's our R group. Are we polar, non-polar, basic, or acidic? Basic means a positive charge R group. Acidic means a negative charge R group. So this is basic, right? Because we have a positive charge R group, a plus charge on the R group. Like I said, don't worry about these charges up here. Those are the same in every single one of them. Peptide bond. So now we know what these amino acids look like. We can draw them. We know how they're distinguished. We know how they're classified. So now the peptide is how we put these together. So they're gonna be put together in exactly the same way we drew them. We're gonna draw. We drew them out, and we drew out NH3 plus. We do our carbon. We do our hydrogen. We do our COO minus, and then our R group. And then we're gonna draw our NH3 plus, CH, R group, COO minus. We're gonna draw them the exact same way, and this. We're going to lose water between it like we done all reaction, and that's going to be our peptide bond. So they're going to all link with the nitrogen on the left, the carbonyl group on the right, and the R group hanging down. So just like we've been drawing them, now we're going to link them together by dehydration reaction. That's right here. We remove water, remove an OH and an H. It's going to be our peptide bond. So proteins are linear polymers of L-alpha amino acids. Let me get these out of the way a little bit here so you can read that. Okay, remember the amino acids are L's. The sugars are all Ds. Okay, so they're L amino acids and they're going to link together. They're going to be polymers. Polymer just means more than one linked together. Okay, carboxyl group of one amino acid is linked to the amino group of another amino acid. Okay, the linkage will be called an amide bond or a peptide linkage or a peptide bond. The reaction is a dehydration reaction. Water is released, just like we've done in hundreds of reactions now. We've done so many dehydration reactions. Okay, so glycine and alanine. We draw the two amino acids. We notice the R group hangs straight down. Okay, off of the alpha carbon. The alpha carbon is the one next to the carbonyl group. Okay, so we're going to take water is, everybody knows what water is, right? H2O. We're going to take H, we're going to take H, and we're going to take O. And you remove these three things to form water. Okay? And we're going to link this CO to this NH, which is right here. So there's our carbonyl group, there's our NH. So that's our peptide bond. It's strictly a dehydration reaction between two amino acids. And the amino acids are, that's why we wrote the amino acids the same every time. That's why I told you. You're always going to write your amino acids just like this. And that way you know exactly where your peptide linkage is. You just take water out of it, like we've done in bunches of reactions. So nothing new here. The hardest part that students have a hard time doing is writing them the same way every time. Just write them in the exact same order, just like we've been doing, and you can't miss it. So this bond right here is our peptide linkage. Now that's become real important in biochemistry because that bond can be broke by certain enzymes depending upon the R groups, how we can digest certain things, and why we can't digest certain proteins. Cellulose. Okay, when you eat cellulose, you can't digest it, period. You do not have the enzymes to break that peptide linkage. Now termites do. Termites can break that linkage and break cellulose. Cows can't do it either, but cows have bacteria in their gut that can break the bond so the cow can utilize those amino acids. So there's a lot of cool things we can do understanding how this linkage is going to work. And just remember, just write the amino acids just like we've done, and the carbonyl group of one end bonds with the nitrogen of the other end because you push them together and you get rid of water. And that's the only way you get rid of water from there. Okay, and that forms your peptide bond right here. This is your peptide linkage or peptide bond. Okay, again, you see the H2O, they got rid of the other hydrogen up there. So the peptide bond or the amide bond, peptide linkage, they're all the same thing. They're all called that. Okay, and then the name of this is a dipeptide. Di means two, and it's a peptide. A peptide is two or more amino acids coming together. If there's two coming together, it's a dipeptide. If there's three coming together, it's a tripeptide. If there's 20,000 coming together, it's a big peptide. We call it a polypeptide because I can say they're named 20,000 different things, okay? But if there's two of them, it's a dipeptide, three is a tripeptide, just for that. And if there's, I think after 10 becomes a polypeptide. Okay, when you name these amino acids, if you're going to write them out, we have a YL ending for the ones that are linked, and then the final one at the end is the original name. Just like when we did our attachments, methyl, ethyl, propyl, we put YL ending, the exact same thing here. We put a YL ending on that. Okay, so everything gets a YL ending except the last one. We name what it is. So we have glycine and alanine. It's going to be glycyl alanine for the name. If we had tryptophan, glycine, and alanine in other order, it'd be tryptophenyl glycyl alanine. Okay, every amino acid except for the last one gets a YL because it's an attachment to the last one, and the last one gets its name. Okay, so dipeptides, those are two amino acids put together. It's a condensation or dehydration, same thing, getting rid of water, between two amino acids produces a dipeptide. Okay. Amino acids with a free NH3 group is the amino acid terminal amino acid, the N-terminal. That's at the nitrogen at the end on the left-hand side. Remember, we always start writing with the left-hand side. So the amino acid with the free alpha amine group is going to be the one on the left-hand side because that's going to have a nitrogen on the end. The amino acid with the free COO group, okay, the terminal is going to have is going to be the C terminal. Okay, so when you write your amino acid, remember we all start with the N on the left and with the C on the right. So no matter how many you put in together, the N terminal is the one on the left, the C terminal is one on the right. Okay, we always written with the N terminal on the left-hand side. Remember I told you, we always start with a nitrogen and we always end with a carboxyl group, carbon. So we put this together. This is alanine and glycine. Alanyl, glycine, or what's most commonly done, we usually don't name them with the YLs and right, because it's too much writing. We just use the 3-letter code, alanine and glycine. Okay. We almost always just use a 3-letter code. When you see it, you'll see this, you'll see that YL ending except for the last one. So when you link it together, here's your peptide bond. This is your peptide linkage right here. That's where they're bonded to. This is alanine on the left. This is glycine on the right. This is your N terminal. This is your C terminal. Because on the left side, N is on the end. On the right side, C is on the end. So when we refer to the N terminal, we're talking about the left side. When we refer to the C terminal, we're talking about the right side amino acid. That make sense? Yeah, okay. I got at least one head nod. All right. So we know the left side, we know the right side, we know the N terminal, we know the C terminal. Okay, we know what YL means in the names and the name at the end, and we use our 3-digit code. It's basically what you're always going to see. Okay, the number of amino acid in small peptides is indicated by the prefixes di, tri, tetra, and so forth. Okay, but you're not going to do that when you get to 50 amino acids or 100 amino acids. We're not going to keep naming that. Okay, so for the basic ones, oops, lost that thing. Okay, dipeptide, tripeptide, tetrapeptide, pentapeptide, hexapeptide. You need 1 through 10, basically. Okay, peptides are named as derivatives of the C terminal amino acid, which received its entire name. So the C terminal is the one on the right side, the N. That one gets its entire name. Okay, all the other amino acids, we change the ending to YL. They're attachments to it. So our C terminal, which you all know now is the last one on the right-hand side, gets its original name. All the other ones linked onto gets a YL ending because they're considered substituents or attachments. And just like in organic chemistry, that's how we name attachments. We name them methyl, ethyl, propyl, butyl, whatever. Okay. The dipeptide, aminoglycine, has the glycine as its C terminal. That's why it has its full name. Okay. Alanyl glycine. There's its full name. It's the C terminal. Okay. So drawing the structures of a tripeptide. Now we're doing tripeptides, which are 3 terminals. So you draw the exact same thing we start with every time. Okay. So we draw our NH3 group. Well, let's do the first step here. NCC, NCC, NCC. We draw our nitrogen, our carbon, that's alpha. This is the alpha carbon right here. And then a carbon at the end. And then we're going to form a peptide bond right here and right here. Okay. And we just add our things to it. We have NH3, we have our carbonyl group, we have our carbonyl group, we have our carbonyl group. Okay. So the same structure as I do now. The only thing we're going to add a hydrogen above each one of these carbons. So there's our structures. They're just linked together now. Those are the same amino acids we've been drawing. And now these are where the R groups attach. Right here, and right here, and right here. That's going to be the difference. I don't care what amino acids you're linking. You always draw this first. This is your structure right here. It's never going to change. It will never change. Okay. The only thing we've done is remove the oxygen from here and 2 hydrogens, the oxygen from this carbon and 2 hydrogens from that nitrogen to form water. and form our peptide linkage. Okay. But that's the structure you're going to start with right here. Every one of these, this is it right here. That's what you draw. Whenever you're going to draw amino acids, you draw that first. That's if you have 3, you draw 4, you add another one. Draw 5, you add another one. Okay. And the only thing we're going to add here, we're going to add our R groups. Okay. Because remember, the R groups are the only thing changing. So we just draw that and we put in the R groups of whatever amino acid we have. So if we want to write alanine, glycine, valine, look on our chart, you find out what alanine is, what glycine is, what valine is. Okay. Alanine is CH3. That's your R group. Glycine is hydrogen. And valine is CH3 twice. Those are the R groups. And this is how it's usually written right here. We usually don't write it like this. It's just too long. We usually write the three abbreviation codes and we leave it at that. But now you'll recognize it if you see it written that other way too. Okay, so then we've added CH3, we've added our hydrogen, and we've added our CH3 twice. And that's it. Now you draw a tripeptide. You can draw any peptides you want now, because now you know how to do it. You're at that exact same chain: nitrogen, carbon, carbon, nitrogen, carbon, carbon, nitrogen, carbon, carbon. Your nitrogen, your peptide linkage, and you put your hydrogen of your carbon, your carbonyl group. You remove water to form each one, and now you just put your R groups attached to it. And that's it. Okay. Write the structure of the following peptides: methionine, leucine, and cysteine. Okay. So you look at the chart, you look at each one, and let's draw the backbone first, then we'll look at the chart. So methionine is going to be, we're going to start with our nitrogen. Let's draw it up here so it doesn't get in our way. Okay. And we have our NH3 plus group of the end. We have our carbon, we have our hydrogen, we have our carbonyl group, and then we have our peptide bond, NH. That's the next one now. Then we have our carbon with our hydrogen, and then we have our carbonyl group, and then we have our nitrogen with our hydrogen and our carbonyl group. No, go back. I'm getting ahead of myself. Our hydrogen, and then our C O minus. So there's our negative charge on the end, our positive charge on the left side. This is our N terminal right here. This is our C terminal. These are all peptide bonds right here and right here. Okay. And now all we have to do is add our R groups. We put an R group here. We put an R group here. We put an R group here. So we look at that we do. So it doesn't, whatever these amino acids are, don't even worry about it. Draw this first. And then go back and look at the chart and figure out what the R group is and just add them. That's it. That's all there is to drawing amino acids. It's all laid out for you. Okay, because the only difference is the R group here. We're going to have that exact same structure for every single protein in the human body. The R groups are going to change. Okay. So we draw this out. This is drawn a bit nicer here, but here's our chain that we drew out. NCC, NCC, NCC. Oops, I lost my marker there. That's what we draw. There's our backbone. Oh, it includes, you should have dipped down and included that. Okay. So we draw our background, our backbone. Okay. And then we added the R groups. We looked up what the R groups were. Okay. And that is the tripeptide for methionine, leucine, cysteine. Okay. We've added our R groups. That's it. Make sense? Cool. Tyrosyl, serol, histidine. Again, you draw the same exact backbone. So you can start with your nitrogen. Remember, we always start with nitrogen on the end. This is our N terminal, NH3 plus. And then we're going to add our carbon with our hydrogen and our carbonyl group. There's your amino acid. Then the next one is going to be our peptide bond. And it's going to be, let's draw in a whole different color. NH, CH, C double bond O. And the next one's going to be in NH, CH, C double bond O minus. Okay. So this is our N terminal because there's a charge there. And this is our C terminal with the charge there. Okay. These are our peptide bonds right here and right here. And the only additions we're going to have to add now are, we're going to put a bond here and here and here. And then we're going to add the R groups. We draw the exact same thing every single time, just like that. Okay, and then we add the R groups to it. Okay. So here's our terminal. Here's our backbone, basically. Okay. For any tripeptide, we draw that NCC, NCC, NCC structure. Okay. And then we have our peptide bonds. Peptide bonds are right here and right here. I was putting it in the wrong place. Okay, so there's two peptide bonds in a tripeptide. And that's where they're cleaved when we digest proteins in food. We digest down to amino acids, we can absorb the energy. That's where we cleave them, at the peptide bonds. That's where they're formed. And so here are your R groups. This is the R group for tyrosyl. This is the R group for serol. And this is the R group for histidine. Okay. So, I mean, same stuff, arginine, isoleucine, and glutamine. Before you even look those up, okay, before you do anything, draw the backbone. Your NCC, 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 and O on the end. N terminals on the left, C terminals on the right. Okay, so before you do anything, you're going to draw this, what I'm underlining right here in red, or outlining. You draw that. That is always going to be the same. It's never going to vary. So once you draw that, then go look it up. Look up each of the amino acids, what their R groups are. And then you add the R groups to the alpha carbon. You add it to the alpha carbon, you're going to get this R group for arginine. You get this R group for isoleucine. And you get this R group for glutamine. So you've added your three different R groups. Okay. Just remember to draw the backbone first, and you'll get it right every time. Okay. So at first it appears logical to think that a long polymer amino acids would undergo constant change in conformation, because remember, single bonds have free rotation. We put single bonds across all those on the peptide background. But that's not what happens. These don't have free rotation in space, because we talked about this before. We talked about, remember, hemiacetals and hemiketals. Remember how we had that bond that would swing down and form those? Same thing happens with these. That's why we did that. Okay. Result in X-ray diffraction. Studies by Linus Pauling actually proved that these bonds don't have free rotation in space by X-ray diffraction techniques. The peptides bond are planar, okay, and rigid. Okay, they're flat bonds that don't bend in space. Okay, because the peptide bond is a partially double bonded character, because it exhibits what's called resonance. Okay, that resonance allows the electrons to move within the same molecule. So this is our peptide right here, our peptide bond, right? Here's our carbonyl group, here's our NH group, and this single bond right here allows free rotation, but it doesn't, because these electrons can come down here and move that double bond to here and move the electrons to here and form a double bond between there. So that's the same structure, just moving the electrons in a different location. Remember our benzene ring had shared bonds that give it its stability. That's what gives these amino acids their stability in the protein chain and locks them into place, because it can share, the electrons can move. And that's what's called a resonance structure. It's just this, we're writing, it's the same thing. All we're doing is moving the electrons. And the electrons can shift between these two forms. Okay, we have the double bond here, or we have the double bond here. Okay, so it's two different forms that both exist in nature. So it's basically a combination of the two, but it's enough of a combination where the resonance structure is shared to give it a stable position in space. Because once you have a double bond, then you can't get rotation, because you got those pi electrons we talked about that lock it into place above the single bond. Okay, so if you've got a single bond, you can rotate around that in space freely. Okay, once you, because you have all the electrons are located here, but now you have pi electrons above it that form a bond above it in the pi electron. This forms your double bond. Electrons get shared, and now this locks us into space. So this cannot rotate, because the second bond forms those pi electrons that lock it into place. Okay, so this means I wrote over on my notes. This means there is free rotation around only 2 of the 3 single bonds. Okay, because those are the ones that don't have shared electrons. Okay, which limits the number of possible conformations for any peptide. So the peptide bond itself cannot rotate. The other bond, this bond here can rotate because there's no way to share electrons here. This bond here can rotate. And this bond on this side can rotate. But the bond right in between, the peptide bond, cannot rotate because it's locked in by the resonance structure. Okay. The second feature of the rigid peptide bond is that the R groups, okay, on adjacent amino acids are on opposite sides of the extended peptide chain. Okay. I drew them, when we drew them, I drew them all on the same side. That's because it's just easier to draw the thing that way. In reality, think of it as that the R groups are going to line up. They're not going to line up next to each other where they're pushed against each other. They're going to line up farther apart so they can fit. I mean, if you're going to line, you're not going to put everything together naturally. It's going to space out to give it the most room it can have. So the R groups are on opposite sides of the peptide chains in nature. Okay, so write the structure of the following peptide at pH 7. There's a neutral pH. Okay, alanine, alanyl, phenylalanine. It's a dipeptide. Alanine is ALA. Phenylalanine is PHE. And you write the same structure we've been writing. Okay, we're going to write our NH3 as our N terminal and our C terminal. Okay, here's our peptide bond between the two. Okay, these are our R groups right here and right here. So this is our background, our backbone. Okay, that's what we always write first before even looking at anything. Okay, for any dipeptide, it's be the exact same thing. NCC, NCC. Okay, the N terminal is going to have NH3 plus. The C terminal is going to have COO minus, and then our 2 R groups. So again, the YL ending means it's the attachment. The name at the end is just the name of the amino acid. For the C terminal, the N terminals, the C terminal is always just the regular name. All the other amino acids are the YL extension at the end. All right, so you're always going to draw the same backbone every single time. You can draw the nitrogen, carbon with the hydrogen, carbon with the carboxyl group, peptide bond, nitrogen, carbon with the hydrogen, carbon with the carbonyl group, and then in this case, it's a dipeptide, so the O minus at the end, and then add your R groups. So it's going to be the same thing every time, same background. We're always going to draw. Okay, this is your N terminal. This is your C terminal. The N terminal is always going to have a positive charge. The C terminal is always a negative charge at physiological pH. All right. So this background is always the same. This is your peptide bond right here. That bond is your peptide bond. It's a dehydration bond. You took 2 hydrogens from the nitrogen side. You took an oxygen from the carbonyl side, and you formed water. Okay. And then the R group, you add your R group for lysine, which is this right here. And you add your R group for alanine, which is your CH3 group. That's how you draw a dipeptide. Okay. This is a tripeptide. Phenylalanine, tyrosine, and leucine. Okay, so phenylalanine, tyrosine, and leucine. Again, you can draw the 3 peptides, CNN, NCC, NCC, NCC. You can draw the same background. Okay, your NCC, your NCC, NCC, and connect. All right, there's your background. Okay, so all we're going to add to your alpha carbons, this is your alpha carbon, this is your alpha carbon, this is your alpha carbon. Oops, that's not what I want to put. I want to go this way with it. Those are all your alpha carbons. And then you're going to add your R groups once you draw your background. Okay, it's always going to be the same. The one nice thing about it never changes. It always starts with the nitrogen, ends with the carbon. And so it's got the same repeating pattern. And the only thing difference is you identify your R groups. That is the R group for phenylalanine, benzene ring with a CH2. Tyrosine, CH2, benzene ring with an OH on the other end. Okay, leucine, CH2, CH3, CH3. And you put your R group. This is how we always draw it. In nature, the R groups are on opposite sides. So if the first one is down, the next one is up. They just be on opposite sides of the double bond just because of spacing, because you wouldn't start cramming things together here. You know, they're going to naturally spread out, can make room for each other. So in nature, it's going to be on the opposite side of the peptide chain. Okay, right. The structure of each of the following peptides, again, at pH 7, neutral pH. Glycine, valine, and serine. I mean, it's usually written glycine, valine, and serine. That's how we normally see it. Just people don't write that out. But you'll know what it means just with the YL ending because they're attachments to the main, to the C terminal amino acid. So you can write the same exact backbone every time. We're going to write NCC, NH, NH. Oops, come back here. All right, so there's a background, right? We always start with the nitrogen, always end with the carbon. Okay, we've always got the nitrogen, carbon with the hydrogen, carbonyl group. Nitrogen, carbon with the hydrogen, carbonyl group. Nitrogen, carbon with the hydrogen, carbonyl group. That's our order all the time of all amino acids. And then we attach the R groups. R group for glycine is H. R group for valine is CH with CH3 twice. R group for serine is CH2 with an OH group. Okay. So remember, glycine is the only one of the 20 amino acids that is not a stereoisomer because the R group is hydrogen. And therefore, the alpha carbon, okay, there's your alpha carbon, that's your alpha carbon is where the R group is attached to. Okay. The alpha carbon on glycine is not chiral because there's 2 of the exact same things attached. Remember, the definition of chiral has to be 4 unique individual attachments. Have to be different. Okay. Dipeptide, threonine and cysteine. Again, you can write your dipeptide chain. You're going to have your N, CH3, CH, N. There's your backbone. Okay, same as always. This is for a dipeptide. Here's your peptide bond. Right there. Dehydration reaction to cause a peptide bond. And then the only thing you have to add is the R groups. You look up threonine on your not the periodic table, the amino acid chart. Okay, and you find this is the R group for threonine. This is the R group for cysteine. And now you have your dipeptide. Tripeptide. You have isoleucine, methionine, and aspartate. Okay. Again, you draw the same exact backbone. Here's your backbone. And we should all be getting this by now. There's your background. And you should be able to identify the peptide bonds or the peptide linkages. Okay, here's your peptide linkage. And here's your peptide linkage. It's always going to be between the carbonyl carbon and the nitrogen, because you've lost the oxygen, and from the carbonyl carbon, you've lost 2 hydrogens from the nitrogen. Okay. And then once you draw your backbone, you look up on your chart, the R groups, and you add the R groups to the alpha carbon. Okay. So it's always the same. Just all you have to really remember is the R groups are the only difference in the amino acids. That's it. Everything else is exactly the same. So everything's going to be the same all across except for the R groups, and you add those to it. The opium poppy and the peptide bonds in the brain. Okay. So the seed poppy is the organelle poppy contain morphine. Okay. Morphine is a narcotic, has a variety of effects on the body and the brain. It causes drowsiness, euphoria, mental confusion, and chronic constipation. Now, it's not addicting because of its chronic constipation. It's addicting because of the euphoria it produces. That's the result people want. Okay. Although morphine was first isolated back in 1805, it was not until the 1850s and the event of the hypodermic needle, okay, was effectively used as a painkiller. Okay, once you could inject it. During the American Civil War, morphine was used extensively to relieve the pain of wounds and amputations. Okay, it was at this time that the addictive properties became noticed. We started noticing that the patients given this became addicted to morphine. By the end of the Civil War, over 100,000 soldiers were addicted to morphine. Because we did that. We said this works as a pain control. We gave it to them, and lo and behold, everybody became addicted to it. Okay? As a result of the Harrison Act in 1914, morphine came under government control. It was made available only by prescription. That'll solve our problem. Put everything under government control, right? Okay. All right. So although morphine is addictive, okay, heroin's a derivative of morphine, is much more addictive, induces a greater sense of euphoria, and it lasts longer. That's why heroin is much more addictive than morphine. We did a couple experiments of that. We've shown what, because heroin passes the blood-brain barrier easier than morphine does, because it is more hydrophobic and can pass through the blood-brain barrier. So it's more, you get a higher euphoria, and it lasts a longer time. So it's more addicting than morphine. It was developed by the Bayer Company in 1898. Heroin is obtained by treating morphine with acetyl anhydride. We use acetyl anhydride, the 2 carbonyl groups, and we're able to take morphine and convert it into heroin that way. Heroin is 4 to 8 times as potent as morphine. That's a lot. Although heroin is converted to morphine in the body, it acts on the brain faster than morphine. When we talk about that, morphine and heroin react to the same receptors. The body doesn't have receptors for heroin. Okay, heroin has no effect on the body. Heroin has to convert into morphine to have an effect. So you would think that morphine would be more addictive than heroin because morphine's already morphine. It doesn't be converted. But morphine in its regular form can't cross the blood-brain barrier, can't get to the brain where the receptors are. Heroin, because it's hydrophobic, can pass through the membranes of the blood-brain barrier. Once it passes through the blood-brain barrier, then heroin gets converted into morphine. And then morphine reacts on the receptors and causes the high. So heroin gets into the brain a lot faster and produces a lot more morphine in the brain than morphine does, because it can pass that blood-brain barrier. Once it's there, then it converts to morphine and does its stuff. So heroin's much more addictive than morphine is, even though it has to convert to morphine once it's in the brain to have to act on the receptors. Okay, heroin has a greater lipid solubility. It's more hydrophobic and crosses the blood-brain barrier much more easily. Okay, this is morphine, and we treat it with acetyl anhydride and heat. And this is heroin. You can see the similarities. Okay, all we've done is added, instead of OH groups, now we've got CCH3, a carbonyl group and a CH3 group. That's the difference. Now, you've taken away the polar groups. Remember, OH is very polar, right? This is hydrophilic. This is hydrophobic because you've taken away the polar groups and now you've made it hydrophobic. So now this can pass to the blood-brain barrier. Once it's in the brain, we take off these acetyl groups right here and put our hydrogen back on, and it becomes morphine, and it becomes extremely addictive because it can get there, produces a much more intense high, and it lasts a lot longer because it gets to the brain a lot quicker. There's no delaying it. Why do they have such powerful effects on the brain? So both drugs have been found to find receptors on the surface of the cells of the brain. Okay, once it's converted to morphine, you can find the receptors. The function of these receptors to bind specific chemical signals and to direct the brain cells to respond. That's what the receptor does in the brain. Okay, it seems odd that cells of our brain should have receptors for a plant chemical. Okay, this was solved in 1975. John Hughes discovered that the brain itself synthesizes small peptide hormones with a morphine-like structure. These are our endorphins. These are what activate your pleasure center in the brain. So we actually have receptors for morphine-like structures. Okay, two of these opiate peptides are called methionine and enkephalon, or metenkephalon and leucine enkephalon, or leukenkephalon. These are enkephalons in the body. Okay, that's what we produce naturally. Metenkephalon. Okay, you can see the benzene ring with the OH, some of the similarities, and this is where it binds to the receptor. Okay, these neuropeptides have a variety of effects. This is the ones produced by our own brain. Endorphins and enkephalons is what we produce. They inhibit intestinal motility and blood flow to the gastrointestinal tract. So they stop digestion. Okay, that's what causes constipation. That's why morphine and codeine cause constipation, because these neuropeptides, one of their effects is they inhibit intestinal motility. So it blocks you up. This explains the chronic constipation of morphine users. Okay. In addition, he thought these enkephalons play a role in pain perception. Serving has a pain blockade. Okay. It doesn't stop the pain. It just tells your brain not to feel it. Okay. Morphine and heroin do nothing to stop the pain. Okay. The pain is still there. It's blinding receptors on the brain that say, hey, that electrical impulse that we're coming up with that says pain, we're going to pretend it's something else. That's all it does. Don't get fooled that these things stop pain. They don't. They just tell your brain to interpret that impulse. Because remember, everything's an electrical impulse coming into your brain. Interpret that impulse as something besides pain. That's what morphine and heroin do, or these enkephalons and endorphins produced naturally in the body. This is where the observation they're found in higher concentration in the bloodstream following a painful stimulation. Okay. When you have painful stimulation, the body doesn't want to go into shock. So in order to prevent that, they start producing enkephalons and endorphins in the bloodstream, going to the blood-brain barrier, past the blood-brain barrier into the brain, and they stimulate the brain and say, let's take some of these impulses and say, it's not really pain. So we don't interpret it as a pain, so we don't go into shock with the body from extreme amounts of pain. That's how our system works. Now, morphine and heroin, we're introducing that to that. We're artificially putting in more endorphins and enkephalons. Okay, they may also play play a role in mood and mental health. Okay, I mean, obviously, you see if you've ever been in a clinic with a heroin or morphine user going through withdrawals, you can see the role they play in mood and mental health. Okay. The so-called runner's high is thought to be brought about by excessively long and strenuous run. This runner's high, marathon, working out, you get to the point where you get this feeling It's usually called an adrenaline rush. But what it is your body starts to produce enkephalins, endorphins, to stop the pain of the strenuous workout. And these endorphins feel good. That's what you feel. And that's a runner's high. Okay, you're producing your own morphine and heroin inside your brain. Right? So unlike morphine, the action in enkephalins is very short-lived. When you do that, it comes back, and by the end of your workout, you're pretty sore. If you really put a strenuous workout, even though you interpret some of it as not being so painful. Okay, but morphine and heroin last a lot longer. Okay, they bind to the cell receptors and induces cells to respond. Okay, then they are quickly destroyed by enzymes in the brain that hydrolyze them. So we have enzymes that hydrolyze, they break that OH peptide bond and they break down that small peptide. Okay, so they hydrolyze the peptides of the enkephalins and endorphins produced by the high. They break the bond, get rid of the endorphin, get rid of the high. Morphine and heroin don't do that. They don't break down like our small chain peptides do. Once destroyed, they're no longer able to elicit cellular response. Okay, morphine and heroin bind to the same receptors and induces cells to respond. So they're mimicking endorphins and enkephalins. Okay, however, heroin and morphine are not destroyed and therefore persist in the brain for longer periods of time at concentrations high enough to continue causing biological effects. I mean, if the high from heroin only lasted 3 or 4 seconds, people stop using it. I mean, it goes way after all, but this light can last for hours. Okay. So I do with cells and coaches yesterday, one mechanism for morphine tolerance and addiction. When the cell receptors bind to enkephalins, the signals to the cell decreases the production of a chemical messenger called CMP. CMP, cyclical, it's cyclic AMP. When we have the endorphins and enkephalins, we slow that down. We decrease that amount. We stop producing it. Okay, so we don't get our signals, so the brain doesn't feel the pain and it feels better. That's one of the effects of it. When we hit those receptors, the decrease in cyclic AMP levels helps block pain and elevates your mood, makes you happier. Okay? You're always happy you don't feel pain. When morphine is applied to the cells, they initially respond by decreasing cyclic AMP levels. So they do the same thing at first. Now the kicker comes in. Okay, with chronic use of morphine, the cells become desensitized. So they don't decrease the cyclic AMP level anymore. So now you need more morphine to get the same high that you did before. That's what intolerance to a drug is. That's what becomes addicting, because you need more and more of it. It's the same as nicotine. It's the same thing. You got to have more because the body gets used to it, becomes desensitized. So the cyclical AMP goes back to normal levels, and now you need more morphine to bring that back down to feel that same high. Okay, so a great amount of morphine will once again cause a decrease in cyclic AMP levels. And then once again, you get desensitized to it, then you need more morphine on top of that. Okay, so thus addiction and the progressive need for more of the drug seem to result from biochemical reactions in the cell. Okay, we can extend this to understand withdrawal symptoms. Withdrawal symptoms with heroin and morphine are extremely nasty. Okay, there's a physical dependence upon it. When an addict stops using the drug, he or she exhibits withdrawal symptoms that include excessive sweating, anxiety, tremors, all kinds of fun stuff. Okay, the cause may be the high levels of morphine. We're keeping the cyclical AMP levels low, reducing pain and causing euphoria. Okay, once morphine is removed completely, the cells overreact and produce huge amounts of cyclical AMP. Okay, so now that all the morphine is gone, the cells go, hey, something's really wrong, and take the cyclic AMP and they dump tons of it into the system. And now your withdrawal system becomes extremely severe. Not just like your regular withdrawal from morphine, but now your body's depleted of it. Okay, it becomes known as withdrawal syndrome, which can be extremely hard to handle. The primary structure is the amino acid sequence, just like we've been doing, of the polypeptide chain. So protein is a polypeptide chain. Poly means many, peptides means each peptide. Okay? Each amino acid is a peptide. Okay, so the primary structure is just the order of the amino acids. As a result of covalent bond between the amino acids, that's your peptide bond. Okay, that's when you dehydration reaction. Each protein has a different primary structure with different amino acids in different places along the chain. Okay, so what makes a protein different? It has a different primary structure because the proteins are in a different order, coded by our DNA. So every protein that's different has a different primary structure. Okay, because the order of the amino acids is going to be different. Okay, it would appear that a long polymer change would undergo constant change because of free rotation around the nitrogen, carbon-carbon single bonds of the peptide backbone. Okay, but they don't because that resonance structure we talked about. In reality, it's not the case. He discovered that peptide bonds are both planar and rigid. Okay, because of the resonance structure we talked about, because you have that bond, carbon, bonded to oxygen, bonded to nitrogen, bonded to hydrogen, bonded to carbon. Okay, this electrons can form down here, forming a double bond and kick those electrons up, forming a carbon-nitrogen double bond, carbon, oxygen, hydrogen, then carbon. Okay, so this resonance structure where the double bond can be here or double can be here forms a rigid place in space. Okay, so the peptide has a partially double bond character which locks it into place. Okay, and this is a better picture than what I drew. So those electrons here, two electrons come down and form this double bond here, and they give you a negative charged extra electrons on the oxygen. So that gives this peptide bond, okay, a double bond character and helps lock it into space. Okay, so there's free rotation, okay, around two of the three bonds. So you still have this carbon-carbon bond, okay, which is not locked space, and this carbon-nitrogen bond. The peptide bond itself, this electrons can swing down here and create a double bond. So this bond here is not free rotation. These other two are, because the free electrons on that nitrogen atom and the electronegativity of the carbonyl group here, pulling the electrons towards it. Okay. Now we told you when we draw it, we draw their R groups. Okay, we draw them all coming down off the backbone. That's not how it is in nature. The R groups alternate. So here's your R group. This is glycine. So there's your R group here. And here's your R group here, phenylalanine. Glycine again. Here's your R group. Okay, here's your R group. Here's your R group. Here's your R group. They alternate in nature. Okay, and this is how we usually do peptides. The glycine, phenylalanine, glycine, alanine, leucine, serine, glycine, alanine. We just use a 3-digit code rather than writing them all out. Okay, but because of this, they're going to sterically hinder each other. There's not going to be enough room. I mean, if we try to move this down here, it's going to interfere with this right here. They're just going to get in each other's way. So it's going to go to the opposite sides, 180 degrees apart, to give it more room. Okay, it's called stereometric considerations. So ultimately, the primary structure of protein will determine its biological form. The order of the amino acids determine where the R groups are, and when the R groups are going to interact with each other, that determines the biologically active form of the peptide. So it's the primary structure that determines its biologically active form, because that's the order of the amino acids. Okay. The interactions on the R groups of the amino acids, the protein chain, depend on the location of the R groups. Depends where they're located, how they interact with each other. These interactions will govern how the protein chain folds, which in turn just takes its final three-dimensional structure and its biological function. Remember, everything functions by shape. Okay, so genes are your DNA code, can change by the process of mutation during evolution. That's how things evolve. That's how we change. That's how we get resistant. How we get a bacteria that's resistant to our antibiotics. Remember, bacteria replicate every 20 minutes. I mean, we replicate every 20 years, maybe a little less, some more than others. Okay, but every 20 minutes, bacteria we go through in 20 years. So every 20 minutes, they're replicating their DNA. If you get a mutation in that DNA sequence, which can occur, does occur, it may occur that folds a protein a different way, so it's not susceptible to an antibiotic, and that's how they get antibiotic resistance. That's the bacteria do it much more quicker than humans do it, because they replicate so much quicker than we do. Okay, the generations are 20 minutes versus 20, 25 years. So mutation in the gene can result in a change in the primary amino acid sequence a protein. If that's what it does, then it can change the shape because it's going to have a different R group. Okay, so over longer periods, more of these changes will occur. The more evolutions, the more cycles of what was I talking about? The more cycles of and during replication, the more changes are going to occur. Okay. So if two species of organism become new species very recently, the difference in amino acid sequencing and the proteins will be very few. So we can trace evolutionarily similar species by looking at the amino acid sequence. Because if they're the same species, and they branch off to different species, their amino acid sequences are going to be similar. There'll be some differences, but the amino acid sequence will be similar. There'll be a few differences. Okay. On the other hand, if they diverged millions of years ago, there'll be many more differences in amino acid sequence of the proteins. So the more recently they diverged apart in evolution, the more amino acid sequences they're going to have the same, because less mutations have occurred, okay, with each generation. As a result, we can compare evolutionary relationships between species by comparing the primary structure of proteins in both species. And the primary structure is just the line of the amino acid sequence. That's a primary structure, just the order of the amino acid sequence in a linear line. All right, that's our primary structure. Secondary structure. The secondary structure comes after the primary structure. Okay. So when the primary sequence of the polypeptide folds into a regular repeating structure, the secondary structure is formed. So the primary structure is just a straight line of amino acids. These amino acids fold upon themselves to become more stable. That is the secondary structure. And it folds in two ways. It's going to form one of two patterns. Okay. The secondary structure results from hydrogen bonding between the amide hydrogens and the carbonyl oxygens of the peptide bonds. Okay, so not all regions have a clearly defined secondary structure. Some are more random or non-regular. It'll form either an alpha helix, which is a helical system like that and bends upon itself, or pleated sheets, which are beta pleated sheets. So it's from one of those two arrangements. I know I'm not a great artist, but we'll have these here in a second. Most common type of secondary structure is going to be a coiled helical shape. The features of it: each amide hydrogen and carbonyl oxygen is linked with a hydrogen bond, locking the helix in place. So the carbonyl oxygen leads to amide hydrogen 4 amino acids away. That's what makes it rotate that turn. Okay, hydrogen bonds are parallel to the long axis of the helix. Okay, it's a right-handed helix. It spins to the right. Okay. The distance is 5.4 angstroms. Angstroms is 10 to the minus 10 if you're in for metric system. It's a very small number, but it's just about 5.4 angstroms has one turn. 5.4 angstroms is another turn. That's every bond between there is 5.4 angstroms apart. Okay, there's 3.6 amino acids per turn. Okay, and this is what it looks like. This is an alpha helix. I know it's kind of weird to look at, but your R is pushed to the outside. Here's your hydrogen bonding connecting them. Okay? And it just takes your primary structure and it starts to fold it in a circle. And it helixes around. And every turn is 3.6 amino acids. So it's like DNA, but just single. It's not a double helix, it's a single helix. And it's called an alpha helix. Okay? And you can see how it forms. It forms this little ribbon-like shape right here. Okay, and every turn from here to here is 3.6 amino acids. Okay, and it folds what's called an alpha helix. Okay, R groups are pushed to the side, the carbonyl group and the nitrogen group, the hydrogen on the nitrogen, form a hydrogen bond. Okay, when it's four amino acids away. Each one that's 4 amino acids away, that forms a bond. And it forms it, and it wraps itself around itself, forming an alpha helix. Okay. Fibrous proteins are arranged in secondary structures of fibers or sheets with only one type of secondary structure. Okay. The repeated coiling of helices So you get your alpha helix, then you get your protofibril. The helices come together and they form this myofibril. And these myofibrils form like one hair cell or one muscle cell. These are units that form together of these proteins. Like your proteins, your hair is made up of proteins, right? So the primary structure, then you get your axial helix forming. These helices link together to form like a braided pattern, and they form what's called a microfibril, and this is what makes up to form like a hair cell. That's how proteins form inside your hair. Okay, so fibrous proteins or structural proteins arranged in fibers or sheets that have only one type of secondary structure. Remember, that's a secondary structure. Your primary structure is a line, secondary structure is alpha helix. If those alpha helix only form one structure, they braid together and form a hair cell, which is a myofibril, what they're called. Okay, the alpha keratins are fibrous proteins that form the coverings like hair, wool, nails, hooves, fur of most land animals. Okay, those are all your alpha keratins. Okay, those are the fibrous proteins that are forming from the alpha helix. Okay, human hair is a typical example of the alpha keratins. Proteins in the hair consist almost exclusively of the polypeptide chains coiled into alpha helices. You have the alpha helix, other ones intertwined within it, and it forms a braided structure, which forms your proteins for your hair. Okay, a single alpha helix is coiled in a bundle with two other helices to give a three-stranded superstructure called a protofibril. Okay, that's part of an array known as a microfibril. So every one of those gets together with two more, braid together to form a stronger strand. Those strands get together and form microfibril, which forms your hair, your human hair. Okay? That's what the protein's made of. Right there's the alpha helical structure. This structure possesses a great mechanical strength and are virtually insoluble in water. Because remember, all the hydrogen bonds on the inside, what's on the outside? All the R groups. All the R groups are hydrocarbon chains. So hair does not dissolve in water, which is good because you don't want to go out in the rain and have your hair dissolve. Okay. The beta pleated sheets. So the first structure we can form is our alpha helix. The second structure for our secondary structure we can form is what's called beta pleated sheets. This is the second most common secondary structure. Okay, remember, primary structure was the amino acids in a straight line in order. Just how they arrange themselves. The list of amino acids in order as they form. Okay. The secondary structure is an alpha helix or a beta pleated sheet. The beta pleated sheet is the second most common secondary structure. Okay. And it's like folds of a fabric. All of the carbonyl oxygens and amino hydrogens are involved in hydrogen bonding with the chain nearly completely extended. Okay. So there's two possible orientations. You got parallel if the N terminals are head to head. Okay, anti-parallel if the N terminals on one chain is aligned with the C terminals of another chain. Remember, chains are listed from nitrogen across. So if you have an N terminal and a C terminal, if the two N terminals line up and form bonds together, forming this beta pleated sheet, then it's parallel. If the N terminal one and then just flips the other one around, the C terminal of the other one forms the N and the C, that's called anti-parallel. And this is what it looks like. All right. So the anti-parallel, or let's turn around. Again, this is your N terminal. This is your C terminal. When they match up, this is anti-parallel. So it's how these beta sheets align each other. One's going this way, one's going this way. Because remember, we always start with a nitrogen end. Okay. If they line up the same way, N terminal, that's called parallel. So parallel beta pleated sheets are on the right-hand side of the screen. Anti-parallel beta pleated sheets are on the left-hand side of the screen, depending how they line up with the nitrogen and carbon terminals. And that's what they look like. So here's your primary structure, and here's a primary structure. And they form hydrogen bonds between them. If the N terminals are together here, okay, that is a parallel. beta pleated sheet. If this is a C terminal, this is an N terminal, then it's an anti-parallel beta pleated sheet. You can see it forms these shapes. And then the sheets just line up within each other, these hydrogen bonds between them. Okay, so now we know primary structure and we know secondary structure. Now we have the tertiary structure. The tertiary structure is an interesting one. That's the three-dimensional shape that occurs when these things fold on top of each other now. So now we either have an alpha helix or a beta pleated sheet. Now the R group is going to cause it to fold into a different shape. That's what's going to form the biologically active form of the protein. So the primary structure is the order amino acid in a straight line. The secondary structure is the alpha helix or the beta pleated sheets. Okay, just how the core of the peptide bonds line up between the carbonyl groups, the hydrogen and nitrogen. Okay, the tertiary structure is a three-dimensional structure. Okay, distinct from the secondary structure, is classified as a tertiary structure. Globular tertiary structures form spontaneously and are maintained by interactions on the side chains or your R groups. So now the R groups form the tertiary structure. Okay, tertiary structure defines the biological function of your protein because everything's determined by shape. Types of interactions that hold this together, that make the tertiary shape, are going to be disulfide bridges between two cysteine residues. Remember, cysteine has an SH group in it. So you can have SS double bonds that hold it together. What's called a disulfide bridge. Salt bridges between ionic sign chains. You have a plus and minus charge. The plus and minus charge can bind together. So you can have sulfur disulfide bridges. You can have polar charges, which are called salt bridges, plus and minus. You can have hydrogen bonding between the R groups. You can have hydrophobic bonding. If they're both hydrophobic, they're going to want to come together. Remember the mycelials that form spontaneously in water. Okay, that forms around drugs that we talked about. When you have a lipid bipolar membrane, it spontaneously forms, it's put in water because the hydrophobic parts want to come together. Okay, so two nonpolar groups are attracted by a mutual repulsion of water. They both repel polar substances that forces them both together. Okay, so this is how a sulfide. Okay, oxidation reduction. Remember, oxidation is the gaining of oxygen, reduction is the gaining of hydrogen. Okay, the loss of hydrogen is oxidation. So we lose hydrogen between these two sulfurs, that's oxidation. Okay, it can go back to split apart by reduction. Okay, so this is your cysteine molecule. Okay, and you can form this disulfide bridge that will connect two different R groups together now. Okay, so this is what starts to happen. So now you have your primary structure, your secondary structure. Now the secondary structure tries to bend into a different form because of the interaction of the R groups. Here's a salt bridge. You have an NH3 plus and a COO minus. Positive and negative charge are ionic and opposite charge attract. That's called a salt bridge. Hydrophobic interactions, two large hydrocarbon chains. Okay, they get pushed together because they both avoid water. They're both pushing all the water away from it and they come together. So there's your salt bridge. There's your hydrophobic interaction. Okay, your disulfide bridge between cysteine molecules. By an oxidation reaction, you can lose hydrogen and form a link between the two sulfur bonds, sulfur atoms. And you can have hydrogen bonds, like the hydrogen on the nitrogen with the carbonyl group, just like what formed the alpha helix, the hydrogen bond. Or you can have OH bonds on your R group, form the hydrogen bonds. Okay, so you have a salt bridge, hydrophobic interaction, disulfide bridge, or hydrogen bond help to form a three-dimensional structure after the secondary structure. Okay, remember the primary structure is just a linear order of amino acids. Secondary structure is determined by the carbonyl group and the nitrogen, the hydrogen and the nitrogen forming in the peptide backbone. The backbone starts to form and it forms those shapes, either beta pleated sheet or an alpha helix. Now the R groups are going to form. Once that group, because the R groups are pushed to the side, The R groups now interact to form either salt bridges, hydrophobic interactions, disulfide bridges, or hydrogen bonding. And that's what forms a tertiary structure. So the R groups determine your tertiary structure. Okay. Now what's left? We have a quaternary structure. We already have our one group, then we have the group full, and then we have our three-dimensional structure already set. So what does quaternary mean? Quaternary is now if you have more than one tertiary structure come together. It forms called quaternary structure of proteins. So the function of forming proteins is not to have a single polypeptide chain, but an aggregate of several globular peptides. So now these polypeptide chains come together. That's your quaternary structure. Okay. The arrangement of subunits or peptides that form a larger protein that get together. Okay. A polypeptide chain having primary, secondary, tertiary structural features that is part of a larger protein. So more than one polypeptide chain come together. That's quaternary. Quaternary structure maintained by the same forces which are active in maintaining the tertiary structure. Same forces in the R group help to connect or form these different peptides together. Okay, so for many proteins, the functional form is not composed of a single peptide, but it's an aggregate, which is a collection of smaller globular peptides. Okay, the protein hemoglobin. Hemoglobin is in your red blood cells, allows you to carry oxygen and carry carbon dioxide. Carry oxygen to your cells, carries carbon dioxide away from your cells. Okay, it's composed of 4 individual globular peptide subunits. Okay, each one of those individual globular peptide subunits is a tertiary structure. When they come together, they form the quaternary structure. You get 2 identical alpha subunits and 2 identical beta subunits per hemoglobin. So hemoglobin consists of 4 chains, 2 alpha, 2 beta. Only when the 4 peptides are bound to one another is the protein molecule functional. Okay? So you need the 4 peptides together in a quaternary structure for it to become functional. The association of several polypeptides to produce a functional protein defines a quaternary structure of a protein, how they all come together. Okay. The forces holding the quaternary structure are the same that hold the tertiary structure. They're the structures from the R group, the disulfide bridges, the hydrophobic interactions, the hydrogen bonding, and the, I'm forgetting one, salt bridges. Okay. These include your hydrogen bonds between polar amino acids, ionic bridges or salt bridges between oppositely charged amino acids, van der Waals forces, okay? Van der Waals forces are your hydrophobic interactions, okay? And your disulfide bridges. Okay. So most of the transport proteins, regulatory proteins, and enzymes are globular proteins. They're made up of more than one polypeptide chain. The very precise 3-dimensional structure of the transport proteins allows them to recognize a particular molecule and facilitate its entry into a cell. So these structural proteins that transport proteins into the cell to allow the cell to survive are very particular what they let into the cell. Okay? The shape allows them to recognize what they can let into the cell and what they can't. So the specific 3-dimensional shape, okay, of the regulatory protein allows them to bind to the receptors on the surface of the target cell. Okay, so because it matches the shape of this receptor, it can bind into it and allow that protein to go into the cell. Okay, in this way, they can communicate from cell to cell, instructing them to take a certain course of action. You have to have cell-to-cell communication, right? Just from your heart to beat, the cells have to all contract at the same time. So cells have to talk to each other. For one cell to make insulin, to tell the other one to make insulin, tell them to stop making insulin when there's enough. Okay, they have to talk to each other. They need this communication, and they do this by receptors on the cell and by these 3 regulatory proteins that match the 3-dimensional shape of the receptors on each cell. It's one way cells can communicate with one another. Okay, so the 3-dimensional structures of enzymes' active sites allow them to bind to the specific reactants and speed up biochemical reactions. Those are what enzymes do. They allow things to bind, come together, and they make the reaction occur at a much faster rate. All right. So this is what you need to know. Primary structure, secondary structure, tertiary structure, and quaternary structure. Okay. You need to know the difference. Primary structure is just the line of the amino acids in order. Secondary structure is the folding of the polypeptide backbone, not the R groups. The polypeptide backbone folds into either an alpha helix or a beta pleated sheet. Once they form the secondary structure, they can fold upon themselves with the R groups now, forming a tertiary structure. Once the tertiary structure is formed, they can form with other chains that come together, again, through R group interactions, the same one, and hold the different chains together. And this becomes your functional polypeptide. And this happens to be hemoglobin, with your 4 units. Okay. You have conjugated proteins. Okay. Nucleoproteins are nucleic acids, like viruses. Lipoproteins are lipids, serum lipoproteins. Glycoproteins are your carbohydrates, like mucin and saliva. Phosphoproteins are your phosphate groups, like casein and milk. Hemoproteins make heme, which is your hemoglobin. And metalloproteins are like iron and zinc, make ferrin and hemoglobin. Remember, iron is inside of each hemoglobin molecule protein. Okay. Describe the 4 levels of protein structure. We should be able to do that now, right? Primary structure is amino acid sequence. That's it. This results from covalent bonding between amino acids called your peptides bond. It's a dehydration reaction between one amino acid and another one. And we'll just put our protein here. I mean, amino acids here. That's not real clear there. Minus. Okay. These come together, always run the same way. You lose oxygen, and you lose 2 of these hydrogens, and you form your peptide bond. Okay. So it's a covalent bond, which is your peptide bond, between the amino acids that link them together. Okay. Primary structure of translation information contained in the genes. Your DNA determines the sequence of the amino acids in the protein. It goes from DNA to messenger RNA to transfer RNA in your ribosomes, and it stamps out and puts these amino acids in order. But the order is dictated by your DNA. That's what dictates the order of the protein. So each protein has a different primary structure. Okay, if it's a different protein, it has to have a different primary structure, coded for by DNA, with different amino acids in different places along the chain. Right? That's the primary structure. Secondary structure is the hydrogen bonding between the amide hydrogens and the carbonyl oxygens of the peptide bonds that are 4 amino acids apart. Different regions of the protein chain may have different types of secondary structure. You can have 2 prominent types, are your alpha helix or your beta pleated sheets. Some regions may have a random or non-regular structure. However, the 2 most common types of your secondary structure are your alpha helix and the beta pleated sheets. Okay, they maximize hydrogen bonding in the backbone of the secondary structure. Okay, so that's primary, secondary, this is tertiary. Tertiary is a 3-dimensional shape of the globular protein as it folds. And that's responsible by the R groups that fold. And there's 4 types of bonds they have. There's disulfide bonds, there's salt bridges, there's hydrogen bonding, and there's hydrophobic interaction. Those 4 things in the R group allow this 3-dimensional shape to occur for this tertiary structure. Okay. The force that hold together, like we said, hydrogen bonds between polar amino acids, ionic bridges or salt bridges between oppositely charged amino acids, van der Waals forces, which are hydrophobic interactions, long chain hydrocarbons, and our disulfide bridges. Those are the 4 forces that hold tertiary structure together. Remember, it's different forces than the secondary structure. It's the forces from the R groups. Quaternary structure is an aggregate accumulation of the tertiary structures. So proteins that have the tertiary structures come together to form a bigger polypeptide, that is your quaternary structure. Okay, association of several polypeptides to produce a functional protein defines the quaternary structure of protein. Okay, the forces that hold the quaternary structure are the same forces that hold the tertiary structure. That's your R group, same 4. What are the weak interactions that maintain the tertiary structure of a protein? Those are your hydrophobic interactions, your van der Waals forces. Your hydrogen bonds, ionic bonds, van der Waals forces, and disulfide bridges. There are 4 interactions, but the weak ones are the van der Waals forces, your hydrophobic interaction. Protein structure and function, types of protein structures and their interrelationships. Okay, so primary structure, amino acid sequence. We're beating this into your heads here, huh? Results from formation of covalent peptide bonds, dehydration reactions between amino acids. Secondary structure includes alpha helix and beta plated sheets. Okay, those are the hydrogen bonding between the carbonyl carbon and the hydrogen of the nitrogen group on the polypeptide backbone, not on the R groups. Hydrogen bonding between amide hydrogens and carbonyl oxygens. Tertiary structure, folding of the entire peptide chain into a 3-dimensional shape, which causes it to be biologically active. Okay, this is because of the different amino acid side chain. This is because of your R groups. And again, there's 4 interactions you need to know: disulfide bridges, salt bridges, hydrophobic interactions, and hydrogen bonding. Quaternary structure is where these tertiary structures come together and add more than one chain into a globular protein. Okay, it involves both disulfide bridges and non-covalent interactions. The same forces that hold the tertiary structure together hold the quaternary structure together. The same 4 forces. Protein function top, follow the shape. Fibrous protein, like your hair, is mechanical strength. It's that interbreeding. As they breed, they form that the breed between the 3 that come together, that forms the tensile strength of this thing. For the structural components, movement. Okay, the hair allows for movement. Globular proteins. So fibrous proteins for mechanical strength, the structural components and movement, like hair. Globular proteins transport things, allow things to go into cells or out of cells. Okay, regulation. Okay, and enzymes allow reactions to occur at a faster rate without increasing temperatures of the surrounding environment. Important peptides and protein hormones. ACTH, androcorticotropic hormone, comes from the pituitary gland, production from the adrenal gland. Okay, angiotensin 2 causes blood constriction to raise blood pressure. Follicle stimulating hormone stimulates sperm production in follicles. These are all peptides that the body needs to work. Gastrin stimulates stomach acid. Glucagon stimulates the liver to produce more sugar. Insulin produces the liver to take in more sugar. Again, this is a positive effect, taking sugar away, or they're producing more sugar. They're opposite effects. Human growth hormone, HGH, okay, bone growth. Oxytocin causes smooth muscle contraction. It's the same as Pitocin. Ever hear of Pitocin drip for induced labor? That's oxytocin. That's what it does in the body. It induces labor, smooth muscle contraction. It also contracts for milk production in the breasts. Prolactin stimulates lactation. Okay, somatostatin inhibits the production of growth hormone. It stops the production. You got to be able to grow and you got to be able to stop it also. Okay, you can't just keep growing. Okay, you got to have positive and negative feedback loop. You got to be able to turn it on and you got to turn it off when you need to and back it up. Vasopressin, okay, decreases the volume of urine by increasing the blood pressure in your body. These are all peptides and protein hormones in the body that have specific functions. So the three-dimensional structure of protein is a feature that allows it to carry out its specific biological function. It's the three-dimensional shape that makes it biologically active. That's the point. That it's the primary structure is the order of the R groups. So the R groups cause your three-dimensional shape. That order is because of the primary structure. Okay, the order those R groups are in is determined by the primary structure. Okay, so the primary structure determines how the protein is going to fold into their ultimate shape. So if we mess up that primary structure by mutation, DNA mutates and put the wrong amino acid in there, that shape can be different. And that's what causes all syndromes of diseases.